Hello. In this video, we will continue talking about chirality, specifically as it relates to molecules. In the last video, you saw that some objects are chiral, basically meaning that they are handed, left-handed or right-handed. In order to be chiral, it has to not have a plane of symmetry, and it has to not be the same as its mirror image. And those will always go hand in hand, so to speak, meaning that if it does not have a plane of symmetry, then it will automatically not be superimposable on its mirror image, and vice versa. So it turns out that actual molecules may or may not be chiral. As we saw in the last video, here is a model of a molecule with 4 different groups attached to a central carbon. Anytime you have that situation with 4 different groups, not just 4 groups, 4 different groups, in this case blue, red, yellow, and white, that molecule probably will be chiral. Now, as we will see later on, there are cases of molecules with chiral carbons that are not chiral themselves, but they have to have more than one chiral carbon, as it turns out. If you just have one chiral carbon, there are 4 different groups attached to the central carbon, then it will automatically be chiral. For example, here is a compound called sec-butyl alcohol. We haven't learned about naming alcohols yet, so you don't really have to worry about the name, but I think you can see pretty obviously where it comes from. Question: are molecules of sec-butyl alcohol chiral? And the answer is yes. You can tell because this carbon has 4 different groups: a hydrogen, an OH, a methyl, and a CH2CH3, or an ethyl group. So hydrogen, hydroxyl group, methyl group, and ethyl group. So question: does this molecule have a plane of symmetry? Well, if you look at a 3-dimensional drawing of it, or a 3-dimensional model, if you just assign each of these colors to a thing, so this is a hydrogen, let's say, this is an OH, this is an ethyl, and this is a methyl, and you will see that there is no plane of symmetry there. No matter how you cut it, you can't get it so that one half of it reflects into the other half of it. So it is chiral. So here are, again, structural drawings of sec-butyl alcohol, 2 different molecules that are mirror images of each other. But the question is it the same as its mirror image? And the answer is no. No matter how you turn this molecule, you could try turning it 60 degrees one way, or 120 degrees the other way, or turning it upside down, or however you want to turn it, it will never look exactly the same as that. So not the same as its mirror image, so therefore it is chiral. Okay, as I said before, carbons with 4 different groups are called chiral centers, or sometimes called chiral carbons, if you know that the center is a carbon. And a molecule with 1 chiral center is always chiral. Now, as noted, sometimes molecules with more than 1 chiral center can be, not always, but can be achiral. I'll give you a little preview. Those are called mesocompounds. Now, let's think about the reality of the situation. Does this mean that they are actually 2 different compounds? Could you separate them from each other and put them into different models? And if so, would the properties of the molecules in one model be different from the properties of the substance in the other model? And the answer is yes, absolutely. All of the above is true. You can separate them from each other, although it's very difficult to separate them because they are so similar to each other in properties. In fact, you really have to have a special technique to separate them, which we will talk about later on. But yes, they can be separated. You can put them into different models. They do have different properties, although, again, the properties in many ways are exactly the same as each other, and we'll talk about those in a little bit as well. But before we go further, let's learn about other ways of representing chiral centers. So these are wedges and dotted lines. This is what's called a Fisher projection. Basically what a Fisher projection is a vertical line and a horizontal line. You don't see any wedges or dotted lines here, so it kind of looks like it's flat. And if it's flat, then it can't be chiral because things that are flat automatically have a plane of symmetry in them. But this is not flat. It represents this molecule here. And the thing you have to remember, here's the key, is that anything that's on the horizontal line is automatically coming out towards you, like the handlebars of a bicycle. You hold on to them, they are parallel to the ground, they're coming towards you. The 2 groups that are on the vertical lines, in this case I've written B and a D there, are going away from you as represented by these dotted lines. So they'd be like the tire, the front tire of the bicycle. So the handlebars, horizontal, coming out towards you, the 2 parts of the wheel going away from you, that's vertical. Why? Well, this is just what everybody has agreed. Fisher came up with this idea, and he said, let's always assume that anything that's on the horizontal bar will always be going towards you, and anything that's on the vertical bar is always going away from you. And what that means, of course, is that you cannot turn this molecule 90 degrees, because then it becomes the opposite. Then what was sticking out in front has to somehow magically go and stick it back behind, and that can't happen. So you can't turn them 90 degrees. You can turn them 180 degrees, because if you turn this 180 degrees, then B would be down here, D would be up here, still pointing back away from you into the plane of the screen, and these 2 groups, C would be over here and A would be over here, still coming out towards you. So that's fine. Turning 180 degrees works, turning 90 degrees, you can't do. Okay, so here's how to think about it. These two groups are on vertical bars, so they will be on dotted lines. These two groups are on horizontal bars, so they will be on wedges. And then what I did was I took this molecule and just tipped it backwards a little bit. Sort of put my thumb on that hydrogen, pushed it straight back into the screen, so there's that hydrogen point back there. This group moves up here a little bit. This group moves up here a little bit. This ethyl group moves in front a little bit. As you push the front back, then the bottom comes up towards you. And now all three of these groups are on wedges coming out towards you, with the hydrogen, which happens to be the smallest of those groups, pointing away from you. So enantiomers, that's the term that's used for molecules that are the same as each other in every way, shape, and form, except they are mirror images of each other, but they're not superposed. So here's a flow chart. Okay, so isomers. What does the word isomer means? It means somehow different from each other, but with the same formula. That means like C3H6O2 or whatever, that kind of formula. There are two main kinds of isomers. Constitutional isomers, in which the order of connections are different, so like sec-butyl alcohol as opposed to T-butyl alcohol. That's as opposed to stereoisomers. Stereoisomers, the order of connections are all the same, but the shape in space is somehow different. Now we've already seen that there are two kinds of stereoisomers. Configurational, which has permanent differences between them. They can't be interconverted by just rotating around single bonds. And then conformational is you can change one into the other one by rotating around bonds. And maybe we should back up and say, when we're talking about isomers, we're comparing two molecules to each other. First question is, do they have the same formula or not? If they don't, then they're not even isomers. Another question is, are they absolutely identical to each other? If they are, then they're not isomers, they're just two of the same thing. But if they have the same formula but are different from each other, then they're isomers. So then you compare. Do the two molecules that you're comparing differ by the order of connections, or do they just differ by the shape and space, but all the connections, what's connected to what, is the same? If that's the case, then those are stereoisomers. Stereoisomers, as I said, have two kinds. In a configurational, the two molecules that you're comparing cannot be turned into each other by just rotating around single bonds. In other words, one chair turning into another chair, or a stagger turning into an eclipsed, or a gauche turning into an anti. Those things are all just rotating around single bonds. Those are conformational. But if it's configurational and they can't be turned into each other by rotating around single bonds, then there are two and only two possible types. They are either enantiomers, which are mirror images of each other, or they are diastereomers, which are not mirror images of each other. It's that simple. So enantiomers are mirror images. Diastereomers, which we will get to in another video, are not mirror images. They're stereoisomers. What's connected to what is the same in both molecules, but they have different shapes in space somehow, and they can't be turned into each other by just rotating around single bonds. We may have trouble imagining how can you have that situation, but we will see here in a few minutes. In fact, we've already talked about cis-trans isomers. Those are molecules on rings in which you may have two groups, both on the same side of the ring, both on the same side of the ring, one on one side of the ring, one on the other side of the ring. In the other case, those cannot be turned into each other. They're not mirror images, so those are examples of diastereomers. We will see other examples of diastereomers later on. Thank you for your attention.